Ever wondered what's happening inside your computer? It's not magic, it's a system of parts working together. Think of it like making a pizza. You need ingredients, a chef, a workspace, and the finished pizza. A computer has four main parts: input, CPU, memory, and output. The input unit is how you tell the computer what to do, like handing ingredients to the chef. Your keyboard, mouse, and microphone are input devices. Without input, the computer would just sit idle. The CPU is the brain, the chef. It takes your data and follows a program to turn it into something useful. The CPU does all the thinking and decision-making, performing billions of calculations per second. Memory is the chef's countertop where the CPU keeps data and programs it's working on. This is called RAM. The bigger the memory, the more tasks the CPU can handle at once. Output is the finished pizza. Your monitor, speakers, and printer show you the results. These four parts, input, CPU, memory, and output, work in a cycle to make your computer function. Every click or keystroke starts a chain reaction inside your machine. The CPU interprets your actions, processes data, and coordinates with memory and output. Without any one of these, your computer wouldn't work. It's a seamless team effort, turning your commands into results. So, next time you use your computer, remember, it's a well-orchestrated system, not magic. Each part is essential for the technology you use every day. That's the foundation of every computer. When designing computers, we use two key terms: architecture and organization. Architecture is like the blueprint of a house. It defines what the computer can do, the instructions it understands, and how it handles memory. Organization is the construction plan, how the parts are actually built and connected. Two computers can have the same architecture, but different organizations, just like two houses with the same layout but different materials. Architecture is the big picture design. Organization is the technical detail. For example, architecture says there's an instruction to add numbers. Organization decides how the circuits actually perform the addition. This separation lets engineers improve hardware without changing how software works. You can upgrade the plumbing of your computer without redesigning the rooms. That's why new processors can run old programs. The blueprint stays the same, even as the materials improve. Architecture is what programmers care about. Organization is what hardware engineers focus on. This distinction keeps computers flexible and upgradable. It's a powerful idea that drives progress in technology. So, next time you hear about a new chip, remember, the architecture is the vision, the organization is the build. That's how computers evolve. Let's look inside the CPU, the computer's brain. Picture a workshop with a main workbench called the accumulator, a special register that holds the number you're working on. The instruction register holds the current command, and the program counter tracks which step you're on. Here's how the CPU processes instructions. First, the fetch cycle. The program counter points to the instruction in memory, and the CPU fetches it. Next, the decode cycle. The control unit decodes the instruction, preparing the circuits for action. Finally, the execute cycle. The arithmetic logic unit, ALU, performs the operation, like adding a number, and stores the result back in the accumulator. This fetch, decode, execute process happens millions of times per second. The CPU breaks down complex tasks into tiny, simple steps. Each instruction is handled with precision and speed. The accumulator-based design is simple but powerful, forming the core of many CPUs. The control unit acts as the foreman, directing the flow of work. The ALU does the math and logic. The program counter keeps everything moving in order. Together, these parts let the CPU run programs and respond to your commands. It's a tiny workshop, working at lightning speed. That's the heart of your computer. Early computers could only run one program at a time, and changing it meant rewiring the machine. Then came the stored program concept, credited to John von Neumann. Now programs are stored in memory alongside data, making computers flexible and versatile. You can load a new program just by changing what's in memory. No hardware changes needed. This is why your phone can run many different apps. Each app is a program loaded into memory. The CPU executes instructions from whichever program is active. Switching tasks is as simple as loading a new set of instructions. This concept turned computers into all-purpose machines. It's the foundation of modern computing. One simple idea unlocked endless possibilities. The CPU, memory, and input-output devices need to communicate. That's where the system bus comes in. Think of it as a set of highways connecting all the major parts. The data bus carries information, the address bus specifies where data should go, and the control bus manages timing and commands. The data bus is like a multi-lane road for information. The address bus is the envelope's address, telling devices where to send or get data. The control bus is the traffic signals, coordinating everything. More lanes on the data bus mean faster data movement. The system bus keeps all parts working together smoothly. Without it, your computer's components couldn't talk to each other. It's the backbone of your computer's internal communication. That's how information flows inside your machine. Computers follow instructions step by step. But what if something urgent happens? That's where interrupts come in. An interrupt is a signal that tells the CPU to pause its current task and handle something important. There are two main types: hardware interrupts and software interrupts. Hardware interrupts come from devices, software interrupts come from running programs. Without interrupts, the CPU would waste time constantly checking every device. When an interrupt occurs, the CPU finishes its current instruction, saves its state, and jumps to a special routine to handle the event. Afterward, it returns to what it was doing. This lets computers stay responsive and efficient. Interrupts are like a fire alarm in a classroom. Everyone stops, handles the emergency, then resumes. They allow multitasking and real-time responses. Your computer can download files, play music, and respond to your clicks, all at once, thanks to interrupts. The CPU never loses its place. It's a clever system for handling the unexpected. That's how your computer juggles so many tasks. Interrupts keep everything running smoothly. All these concepts work together like a symphony orchestra. The CPU is the conductor, the system bus is the air carrying the music, and the stored program is the sheet music. Hardware is the orchestra, software is the music played. Interrupts let the system respond to surprises without missing a beat. This teamwork lets your computer multitask and adapt. Every part has a role, following rules that make the system powerful and flexible. Next time you use your computer, remember the symphony of science and engineering behind the screen. It's not magic, it's brilliant design.